Hello everyone. In this video I want to show you how to calculate reaction rates, okay, through something called the rate law. All right. So when we talk about this, just as a little bit of review, remember we are talking about the concentration of the change in concentration over time, and we always measure the disappearance of the reactants, not the appearance of the product, and this is called the instantaneous method. Um, as you can see here, the instantaneous rate using the instantaneous method is found this way. Okay, the initial rate is all that we measure. Okay, so we're going to standardize this. It's just a standard way of measuring this thing at the beginning. You can see here the disappearance of the purple is what we're looking for, not the appearance of the green. So the disappearance of the drop in A is what we're looking for, whereas not the appearance of B, which is seems to be our product. Okay, so when we have our reaction, it's going to look a little bit like this, a lot like this. This is called a rate law. Okay, this is called a rate law, and the rate is, of course, the disappearance of the reactants right here. Okay, this is the disappearance of the reactants, or at least that's what we're calculating for. Then we have to find K. All right, we have to find K. Not only do we have to find K, but we also have to know the label for K. That's a big deal. This is one thing that I'm going to be a stickler on, and also they're asking for this on the test. You must know the label for K. All right, this is kind of complex, but it's a little bit of math, and we should be able to get that done. From now on, whenever you see brackets, a set of brackets, that's equal to concentration, which is equal to molarity. Okay, from now on, that's moles per liter. Brackets are moles per liter. That's a standardized thing in chemistry. The reaction orders, that's something new. This is raised to the M and raised to the N. That's the concentration of reactant A and the concentration of B, reactant B raised to the N power. Okay, those are called the reaction orders. Together, when they add them together, they create what's called the overall reaction order. It's the sum of the two. This is important because we need to know what kind of reaction we have. There's something called a zero order, and then there's a first order, and then there's a second order. And there's actually more than that, but it gets a little bit more dicey after that. Okay, so let's talk about large K values. If we have an extremely large K value, 10 to the 9th or better, fast. Small K values, 10 or lower is a slow reaction. So your next question is what about somewhere in the middle? Well, we got to figure that out, and we got to look at some data in order to determine the speed of that. So this is a typical experiment done. Okay, you'll notice that there's 3 reactions, experiment 1, 2, and 3. I'm sorry, 1 reaction with experiments 1, 2, and 3. And you'll notice that these experiments are going to help us set up what is called our rate law. Now, rate law, the orders can never be determined through stoichiometry. You must look at data in the form of experiments in order to do this. And what we're going to do is we're going to figure out our rate law, and our rate law is simply rate is equal to reactant A. I use X and Y raised to the X times the reactant B, the concentration of reactant B raised to the Y. I know the last slide had M and N. I use X and Y. No big deal. You can use whatever you want. So I got to figure out all portions of this. Oops, I forgot K. You got to put the K constant in there, the rate constant. Anyway, I got to figure out all portions of this. So when it says A, determine the rate law, it seems real simple, but it's actually a lot of work. But it's not too bad, and you actually get real used to seeing the numbers the more you do this. So what I'm going to do is I'm going to compare experiments, and I'm going to keep the numbers simple. I'm going to keep them as whole numbers, and then I'm going to work out the values for X and Y. Okay. So what I'm going to do is this. I want to keep some things constant, as much constant as possible, and vary only one thing at a time. So if I compare experiments 1 and 2, I notice that this stays constant while this concentration of reactant B changes. But again, I want to keep whole numbers. So what I'm going to do is I'm going to take everything from experiment 2 and divide it by experiment 1. Okay? And the way that's going to work is this. So let's take this whole line of experiment 2. Okay, so the rate is 8.0 times 10 to the negative 5th molarity per second. I guess I didn't need parentheses there. Is equal to K, which we don't know yet, times the times the concentration of reactant A raised to the X power times the concentration of reactant B. I'm sorry, I said experiment 2. No, we're right. 0.200 molar. I got a little ahead of myself. And now I'm going to divide that by everything from experiment 1. Okay? Well, so experiment 1 is 4.0 times 10 to the negative fifth molarity per second is equal to K, which I don't know yet, times the concentration of reactant A raised to the X, times the concentration of reactant B, hold on, times the concentration of reactant B raised to the Y. Okay? Now, let's cancel out everything that stays as 1. Okay, well, this is the same as this. So 8 over 4 is 2 is equal to, those will be the same. So those equal 1. This all equals 1. But this equals 2 again, 2 to the Y. Well, Y must be equal to 1 to get 2 again. Okay, 2 to the 1, 2 to the first gives you 2. Okay, so I just figured out Y. Okay, again, go back and pause if you need to. So now I know Y. Y is 1. Okay, you can put 1. You don't have to. You can leave it blank if you want. Okay, typically we just leave that blank. I put it in there just for demonstration purposes. So let's do the same thing, but now solve for X. Keep some things constant. But now we got to keep the other one constant. We got to keep the reactant B constant. Okay, so now let's take and compare. Let's get rid of some garbage. Let's take and compare 3 to 1. Okay, 3 over 1. So reaction 3 over reaction 1. Experiment 3 over experiment 1. So I have 8.0 times 10 to the negative fifth is equal to K times 0.200 molar raised to the X times 0.100 molar raised to the Y. I could plug in Y there. I can leave it blank. It doesn't matter. It's going to be equal to 1 anyway. Okay? Now, experiment 1 is, let's see, that's molarity per second. 4.0 times 10 to the negative fifth molarity per second is equal to K times 0.100 molar X and 0.100 molar Y. Okay? Move this down a bit. So, solving for what we see here, if you're good, you can do the mental math. If not, let's check this out. This is all the same. That's 2 again. That's K. This is 2 to the X. This is all 1. So again, I'm just not writing the 1's down here. So X is also equal to 1. Okay, that was nice. X is also equal to 1. So if I write my rate law, knowing everything now, and that was all work for part A, this is the answer to part A. Rate is equal to K, which we don't know yet, times the concentration of A times the concentration of B, DUN done for part A. So you would say, what is the order of reactant A? You'd say first order. What is the order for reactant B? You'd say first order. If the question is what is the overall rate law or what is the overall order, you'd say it's second order, because 1 plus 1 is 2. It's second order. Second order. Okay? Next, let's solve for part B. Part B typically says, what is the value for K, or solve for K, and what is the units? Okay, we always have to have the units for the rate constant K. So what I do, now that I know my rate law, I usually just go back to experiment 1 and plug and chug. So that's rate is equal to K times concentration of A times concentration of B. Those are brackets in my world. Okay? So 4, oh, didn't mean to do that, times 10 to the negative fifth molarity per second is equal to, let's see here, that was 0.100 molarity times 0.100 molarity. And where did I get those numbers? I used experiment 1, 0.1 and 0.1. Okay, there you go. Now watch what happens here. 4.0 times 10 to the negative fifth molarity per second oops, I forgot K. I did that again. Times 0.0100 molarity squared. Yes, you have to square your labels too. You have to square your labels too. Okay? Now, let's get rid of that and solve for K. So I'm going to divide out by 0.00100 molarity squared. Okay? That gives me K is equal to this. Now let's be careful. We can come up with a numerical value very simply. So 4 times 10 to the negative fifth divided by 4 times 10 to the negative 3, I believe is 4 times 10 to the negative 2, or 0.04. It's 0.04. So that's our numerical answer. But what about our value for our K value? I'm sorry, what about the label? So anytime I divide by a number, I can flip it and multiply by the reciprocal. So what if this is over 1? Okay, let's just remember all this stuff here. Well, so let me just flip this over and put it up here. So I'm going to multiply by 1 over, this is the reciprocal, 0.00100 molarity squared. Well, if that's the case, I have molarity canceling out with a molarity, and therefore I have just molarity to the first. So my answer, I know this is confusing, but you got to work through this. My answer is still 0.04, but it's per molarity times seconds. Okay? Don't be confused. If they list it as 0.04 molarity to the negative 1 times seconds to the negative 1, it's the same thing. Don't be confused. If they list this as, just reference this real quick. If they list it as 0.04 liters over moles seconds, that's just the reverse of this right here. It's just liters over moles, okay? Because it's moles per liter, okay? 3 ways to do it. It's no big deal, okay? That's it for now. Email me with questions.